How you guys doing? Guys ready for the break? It's been a weird semester. We had the IDA come through, and then it's like no more breaks. So, just realizing that this is like our first actual break for the semester. Technically, it was the planned one anyway. I traveled at the very start of the semester, so for my other classes, I missed the first week. I recorded one online and then just like skipped one, and I was just going to catch up on the material. Then I came back from my traveling right as IDA was coming. Just sent my semester into a tailspin from the start. It's been a crazy one, and then I traveled again when we were supposed to have fall break, and I was supposed to, I was going to host like one lecture online, but then we were supposed to do like both there, and it was just been a little bit of a mess. And now, you guys have the rest of the mess here. So anyway, hopefully it won't be so much a mess. Today, wanted to pick up where we left off. Yeah. Oh, good question. I'll go ahead and pull up Moodle and show you essentially where I'm putting stuff. I kind of need to check it to tell you anyway, so just give me one moment. I posted all my former slides and a link to my YouTube, the playlist that covers all of the classes that I taught for the other section of 3110. So if you are interested, if you want that as a study material, I go through problems and stuff. I can't guarantee that's going to be a good port to what you've learned, but maybe it's a good supplement. So I'm bringing up Moodle. Just give me one moment. All right. So here's our Moodle page. Essentially what I'm doing, you'll see materials from other 3110 section. That's, if you're interested in seeing any of that former material, you can go to the YouTube playlist. I have a new playlist for you guys, so whenever I upload any videos from this particular class, it'll go to the other playlist, and then I post those links directly to those videos. But I just wanted to put that playlist there because then you can see the matching ones for any of these lectures that I covered in my other class. Okay, so that's the supplemental. What I'm putting in here for the current content is under this wastewater regulations in microbiology. I might put a separate one for BOD or just kind of expand that to include everything for the rest of the semester, because today and next time. So I put the intro to wastewater slides that I went over with you, the permit writers course, that Cuyahoga River article, and I intended to put the secondary treatments slides from last time here. Looks like I didn't yet. I apologize. I thought I had done that, and I thought I had posted the... You know what? Maybe I put them in... I think these were from BJ. Yeah. So I don't think I've added anything here. Yeah. I think I'm just leaving the sections he had there by themselves. I intended to put these slides up. I apologize. It looks like I did not. But I will be putting them in this section like I did for the intro to wastewater. Okay, so I'll try to do that after today's class, so you have that. And I will post the video links as well when I get the chance to process them. I don't know how much bandwidth I'll have over the Thanksgiving break, some traveling. Okay, so that's where you can find it. Any other questions before I get started? All right, so again, these slides will be up after this class. I'm not interested in going through part C here. I would rather just kind of plow through the other material today. It's another mass balance problem. I'm not expecting you guys to know mass balances because you guys apparently didn't learn it in that manner. Just FYI, we did a mass balance on the concentration of the bacteria to find the substrate, because it kind of worked out that way. This one, we'd have to do a mass balance on the substrate, and that'll, now that we know the substrate, we'll get an equation that contains some, calls back that substrate concentration that we solved for in that previous part of the problem, and we can get that to find X. Okay, and if you'd like to, you can see my recording for the other course. I did solve that, but again, I'm not expecting you guys to know that for the final exam because you just don't have the context. So that's the tail end of, I just wanted to wrap that one up right there before we get into today's lecture. The blank notes are posted for this one on Moodle, in case you wanted to follow along with those notes. Okay, so wanted to talk, last time we kind of introduced secondary treatment generally and talked a little bit about some of the things I'll cover in more detail today. But essentially last time we looked at the math for a case where there was no recycle line, right? That was the mass balance situation. Technically, the mass balances in a way are more complicated when you have recycle, and the dynamics of the system, you maybe compute that with MATLAB code or something like that. I had a graduate project in one of my graduate courses on wastewater to do just that on several different types of bacteria that were the most common ones. How quick are they growing? What rates are they growing, consuming stuff, all of that. However, we can take a few things and look at it on a simpler scale in terms of what mass of bacteria are in there, and really tracking and comparing the mass of bacteria that are in there compared to the flow of substrate through the system. So that's kind of the approach we're going to take, likely more along the lines of what you've done in the semester so far. Here's an equation that applies to this system that we can use to know more about the system. Okay, so I want to go through a few assumptions when we are using an activated sludge system like this. There's several assumptions we can make and ought to make in order to describe this activated sludge system conveniently, I'll say. First thing, and I think I mentioned this last time, is we have this clarifier, the sedimentation tank after our aeration tank. And what we're going to assume is it does a perfect job collecting all the solids, all the X. So all of our bacteria mass that's going to be recycled is caught here. And we have some concentration then that X is going to either be recycled or sent to waste. And so we could say this is XR or XW. Doesn't really matter. And in fact, the diagram I've got here says XR here and XR here, just using the same thing. Nothing happens if you split a pipe here. You're taking water and splitting it to two different directions. There's nothing that changes the concentration there, unless maybe you had a membrane. But there's no membrane here, so we have no difference there. It doesn't matter how much we send to waste and how much we send to recycle. It's the same concentration. It sounds really obvious, but I just wanted to clarify, make sure that's clear, that if you know the concentration in any one of these three spots, it's the same throughout each of those pipes. Okay, the other thing that is important here is when we assume that it's perfect, that means this XE goes to 0. And I have that written up here, just kind of highlighting what we're talking about there, especially because that might be a little small. So that means our clarifier removes all of the bacteria. Now, there are cases in operation when you have something that goes wrong. Maybe you accidentally shock the system, the pH changes abruptly, the bacteria get thrown all out of whack. A different type of bacteria starts growing and dominating the population and produces lots of bubbles, lots of suds and filamentous byproducts of their digestion, and causes lots of the bacterial mass to float. This is called sludge flotation. It's a very bad thing. We never want that to happen, because then our system is no longer operating like we expect in terms of these mass balance principles. And we're sending loads and loads of bacteria out to the effluent, which we were trying to avoid in the first place. So it's a complex problem. We'll talk a little more about that in a minute. The other thing we assume is there's no biological activity here. That's not true. there's going to be some biological activity, but we're not bubbling air through it and promoting and activating this growth. So effectively, since we're not adding all that oxygen and the water's not there for a whole long time anyway, that means that for our purposes of mass balance type of considerations, what volume is this process happening in, this volume practically goes to zero in terms of what matters for the process. Okay, so I'll say volume for the process, I guess. We can kind of think of it that way. That it's not going to contribute to our calculation for how long water is in the system in terms of a hydraulic residence time. So we assume no reaction. So it's not technically a zero volume. It's not technically no bacterial activity in there, but for an assumption, it's handy. Okay, the other thing to note here is since this clarifier, the only thing it's changing is the solids. It's not changing the dissolved constituents, right? Just like I mentioned a minute ago, if you have a pipe, you split it two ways, nothing's happening, nothing's changing. The clarifier, it does change the amount of solids in the system. We are assuming that it changes it so that all of the solids goes down and none escapes. Now, if we track S, the dissolved substrate, the food, the junk that we're trying to biodegrade, well, we'll have some S in here, and that same S is going to leave here, and that same S is going to go over here, which means that's the same S here and here, right? So all that to say, obvious, but the substrate concentration in this system is not changed by the clarifier, and so that's just going in any of those directions. So the S in the effluent is equal to the S in the reactor, which is S in the recycle and all that. Okay, and then the last part, I already mentioned this, XR is equal to XW, so the recycle line is the same as the waste line. And the other thing to note here is because we assume XE is zero, we know that the X in this recycle waste line must be higher than the X in the actual chamber, right? We are concentrating it by separating the sludge from the water. That's doing a concentrating effect, and we know that we're just taking a little bit of the water with that sludge. It's sort of a slurry, and just by sedimenting the particles, it's going to actually be mostly water, but certainly at a higher concentration of sludge than what we had before. Okay, so there's some basic assumptions about our system that are going to allow us to have a couple of equations that really help us describe that equation or these processes. Okay, and this first one would be the food to mass ratio. And if you think about it, in terms of, I guess, practical matters, how much food versus how much bacteria you have relates directly to that principle where we talked about that the amount of food dictates how quickly they're going to grow. So we talked briefly about microbial growth kinetics with that mu, where that mu depended on substrate concentration. We had some mu max, and then a couple other things here, Ks plus S, all that stuff. It depends on S, depends on how much food there is. And then the growth rate, so if we're talking about the rate of growth, was mu x, right? So it also depends on X. So the fact that the rate at which bacteria are growing depends on how much bacteria we have and how much food we have, shows the importance of this food to mass ratio because it's going to kind of determine how much food really is available to them. And this is actually on a daily or some time basis. So the units here are not just food divided by mass. It's actually a rate of how much food do they have on a daily basis to be growing on. One thing I'm going to say here is I put this F to M in quotes because I'm labeling this, and our textbooks typically do this. I'm labeling it as one parameter. This is the food to mass ratio. It is a ratio. I'm not interested in separating the F and the M. Okay, so when you look at this in an equation, again, I'm going to post the equation sheet that I would normally give to my class so that you can take whatever you need from there and put it on your equation sheets. So this one will be up there, and what I'm telling you now is do not separate these. If you are manipulating algebraically, keep it that as one thing, one object. Do not multiply m to both sides, okay? Just keep it as it is. So that's just one parameter. All right, so that said, what is it? Well, it is the flow rate times the substrate concentration that's coming in, so QS naught. That's essentially the mass per time of food. And we divide that by the volume times the concentration of bacteria. That's the mass of bacteria, because concentration is mass per volume. Multiply that by volume, you get mass. So that's pretty straightforward. What we're talking about is that amount of food coming in per time divided by the amount of bacteria that we've got there. Okay, I mentioned a minute ago the fact that we want to keep our bacteria happy and healthy, and the right bacteria happy and healthy. If we accidentally starve them, that's another condition where some bacteria are going to grow better than others. Bacterial growth, if you get into the microbiology of it, there's all sorts of interesting things that happen. There's, of course, millions of types of bacteria in a wastewater system, all sorts of bacteria going in there, and there's potential for any of them to grow, right? But bacteria, some bacteria thrive when they're starved for a time and fed for a time. Some bacteria like just having food all the time. So depending on what type of niche that bacterial type can excel at and dominate its environment in, that's going to dictate kind of what they prefer. So we have identified several classes and several common species that normally grow in a wastewater treatment plant, and some have been identified as, oh, this one could be a problem if you grow too much of this. You'll get that filamentous stuff that if it grows up too much, then you get a waste flotation, a sludge flotation event, and that's a very bad situation. So all that said, you want to get a good range for your population ecology, as well as for keeping your waste consumption rate as high as you need it for your actual treatment, because both are going to depend on that food to mass ratio. Okay, and the food type, by the way, also matters. If you had a sudden change from your typical municipal, sewer influent to maybe some other industry, maybe a lot of oil and grease from restaurants or something suddenly comes into your wastewater treatment plant, you might have an issue where suddenly a different type of bacteria are needed to account for that, and either that change in bacteria could be a problem, or just simply the fact that the current bacteria are not capable of eating all those lipids and processing it, digesting it like you need. That could also be a problem. So there's a lot to consider there, just on the conceptual level for wastewater operation. Okay, so the next topic then is, and I alluded to this a little bit earlier, is hydraulic retention time. So in a system, in one of these systems, I'm sure you guys have talked a little bit at least about hydraulic retention time, the basic principle of how long is the water staying in your system, and it's V over Q, right? So it's maybe you called it tau for that lifetime of water in the system. I've been using theta, but regardless, this is essentially that residence time of water. And you can get that by taking V over Q. So this HRT does not actually change when we start recycling because of that assumption we said earlier, where there's no reaction, or there's assumed to be no reaction here, or not. When I say no, let's just say there's no significant. It's not a significant contributor to the overall reduction in S. So that means our volume is just the aeration tank volume. Keeps it simple. Q, then you would think that the flow rate is going to change. You might think that because of your recycling, and so therefore you're adding a new Q here, whatever that recycle rate is, and so you have a faster flow through it, but in reality, if you draw the control volume outside of that whole recycled system, in essence, the water is flowing through this system at a rate of Q coming in and that same Q going out, but that's split between QE plus QW. So the QE here and the QW here. So in essence, the same, like some of it, yeah, goes through, and so it's kind of a faster rate if you're just looking at like the flow speed through this chamber has increased a little, but since you're recycling some of that, the net is the same as if you had this flow, right? So that's what's happening here, and if we draw our control volume for this system in that manner, that's what we end up seeing. The control volume is a concept specifically for mass balances. I don't know if you talked about it, but you're really looking at whatever's happening across the borders of that volume, right? So at those spots I just highlighted, those are the only things that are crossing in and out. So that's defining what our inputs and outputs are. And then the reaction is whatever's reacting inside of here. And we already assumed that no reaction in our clarifier. So that leaves just the volume of that aeration tank. Okay, does that make sense? All right. So hydraulic retention time essentially is unchanged. Doesn't matter if you add recycle or not, but the solids retention time does change. And what I mean by solids retention time, it's the same concept, except now we're talking about, instead of the liquid itself, we're talking about the solids in the liquid. And this is changed because we do have a separation here with the amount of sludge being accumulated here, and we don't have that output of sludge. XE over here is 0. Okay, so when I described the solids retention time, you could also call it the cell retention time, because it's like bacterial cells. So you'll see it theta C. You might see it as SRT or cell retention time. This is not the same as the hydraulic retention time if we have got the recycle system. If there's no recycle, it's essentially the same. Water's just flowing through, whatever's in there is in there, and it's just going, right? But in this case, this cell retention time for a recycle system is going to change. It's not going to be the same, right? So that's kind of just what I'm highlighting here. So what is it? Well, you can think of, if we got V over Q for our water, and then we want just the amount of bacterial mass in that system, then what we could look at is to say, okay, well, instead of the volume of water spending time in the system, we just multiply that by X. And so if we had V times X on the top and V and Q times X on the bottom, but this was Q total, then we'll rewrite this as Vx over the QW XW plus QE XE. So really just catching the total travel of bacteria in and out of the system, kind of adding that to the V over Q equation, to the hydraulic retention time. And so that's essentially looking at the bacteria going through here and here, and tracking it that way. So when we write it, well, one thing we'll notice is the XE goes to 0 because we assume that the clarifier is working pretty much perfect. So that's helpful. And it just becomes, our equation here is Vx over QW XW. And so one thing you might notice here is this solids retention time is in a way controlling the amount of X we have in our system. If we change the flow rate of how much we're sending to waste right here, then we're going to affect directly the amount of X in our system. So that QW, it turns out, has a lot of control over our systems. If we want to adjust these parameters, if we want to adjust food to mass ratio, we can do so by adjusting the amount of bacterial mass in the system. We can adjust that by sending more or less bacteria to the landfill. Okay, so that's really a big design parameter for secondary treatment, this activated sludge process. You can have other systems that, instead of a aeration basin and a clarifier, there are systems called membrane bioreactors where you actually use a membrane to keep the bacteria in, and you essentially do filtration at the same time as this aeration. It's not as common, it's a little more expensive up front, but it's great treatment. You can actually have a higher bacterial concentration because you can do better and faster with filtration than you can with a sedimentation chamber, and with less land area. There's just some other costs for operation and installation. But essentially the same procedure or principle applies, controlling how much bacteria or sludge you're taking away then, rather than leaving it stay in there mixing, will control you at that cell retention time, and we'll control those parameters. Okay, so that's just a little aside. Right now we'll just consider the recycle system, and we've got an example problem here. So part of this problem is going to talk about a non-recycle system. Like I said at the start of today's class, I'm not expecting you to do the mass balance analysis. So I was not interested in you doing that full problem. And my plan is that I'm not going to test you directly on the non-recycle system. Okay, so that I'm going to go ahead and say that now. I'm going to get the equation sheet that I'll give you has the derivation for the derived equations for the mass balance on these. You can probably just go ahead and ignore them. So I wanted to talk to you about that, then I learned that you hadn't really covered mass balances, so we're going to kind of go light on that part. This problem then kind of follows that example, and the first parts of the problem, well, we'll go through A, but then the next ones are pretty much exactly like that example problem from the end of last class and what I kind of summarized at the start of this class. So you can take a look at that if you wish, but I'm not thinking that's going to be terribly important for you to study. I'll think about whether or not I want to do anything with the growth rate stuff. I might design some sort of question that doesn't require mass balance, but is testing you on some of the growth rate stuff. So it may be worth looking at this and where those pieces would fall in. I'll give you an update on that next week. Okay, so for this problem, here it says consider a wastewater treatment plant that's being renovated, essentially going from a non-recycle system, maybe like a pond or something, to an activated sludge recycle line system. We're assuming that the incoming bacteria is 0 to the plant without the recycle line, like that example problem with the pond, and then we have to solve a few problems. So part A says draw a schematic for the system before and after the recycle line. It's pretty obvious, although I would say we probably ought to have a clarifier here, which you might not have thought about. So the secondary treatment here, you'd still want the clarifier there to remove whatever bacteria did grow. Okay. Then the recycle system, of course, is going to be exactly what we've been seeing with the recycle line. Clarifier here. Do that. Something like that. Okay, so that would be our recycle system. All right. Part A is exactly like that example problem from last time, as is part B and C. So we're going to, that's part B, C, and D. So I'm going to skip that. If you'd like to, go for it on your own. But what I'm interested in then is for part C, for you to go ahead and take a minute and see if, based on what we covered today so far, you can answer this. Is this large enough font for you to see towards the back, or do you need something bigger? It's okay? All right, so this part E then says, if if the sludge produced has a concentration of 12,500 milligrams per liter VSS, which is now recycled into at a flow of 150 cubic meters per day, what is the resulting, quote, influent MLVSS concentration in milligrams per liter VSS entering the aeration tank? And the hint here is to refer to the drawing, so go ahead and draw it, and label the components so you know really use that drawing to figure out what the question is asking before you try to answer it, okay? I'm going to write up the equations that we've had, sketch a drawing for yourself, challenge yourself to see if you can address this problem given what you know. And by the way, you do have all of the tools and equipment to solve the problem. It might not make sense, so just challenge yourself to see if you can catch it in the next couple minutes, and then we'll go over it together. Okay, so got a chance to take a look, to think about it. I went ahead and drew up a picture and then decided I needed a bigger picture. So I wanted to highlight exactly what the question is asking for here, with a bit of room to write on it. And so essentially what we're looking for is the amount of X going into our system from right here. So this point, how much X do we have before it enters the system, but after the recycle line has merged with the influent. So the deal here is, if that's the X that we're looking for, we have in that line right there, our Q is QR plus Q. So what we're dealing with is a mass balance type of situation just right here. And I know we're intentionally going light on mass balances, but this is totally simple enough. You can do it intuitively. You don't need to call it anything fancy. What we're looking at is, well, what's the concentration in that pipe if we know something about the concentration in the flow in this pipe and something about the concentration and flow in that pipe. It turns out we don't even need any of the equations we just talked about. We just need to know what the system is doing and how to draw on that system. So given that, what we need is to say, well, the total amount of X in this new pipe doesn't change from the total amounts coming into it, right? It's just two flows merging in, and we have one new flow. Very simple mass balance that you could do intuitively like this. You could say that and I'm going to call this X naught prime. You could call it what you want. That's just what kind of made sense to me to describe what we're looking for to solve for, multiplied by the flow rate, because if we ever take a concentration times a flow rate, that's a mass per time unit. It's very handy in mass balances. It tells us something about how much mass we've got there. If you did that with a volume instead of a flow rate, it's going to give you the mass, right? It's just a very simple way to quantify how much mass is there. So we'll often be doing this, and the flow rate here is going to be that QR plus Q, because we have those two pipes come together. So those are our flows, and that's going to be the same amount of mass per time if we were to add the amount of mass coming in from the QR XR and the Q X naught. So we'll say that is equal to QR times XR plus QE, not E, sorry, Q times X naught. Now, we know that X naught is 0, so that kind of simplifies things. This goes to 0. And we can solve for this by saying X naught prime is equal to this QRXR divided by that total flow rate. Okay? I have given this problem on an exam some time ago, and there were a lot of students that got it wrong because they jumped straight to trying to use one of the equations on the equation sheet without first identifying what really was it asking for and how would you approach it, right? If you hopefully took a look and identified this is the spot where you're trying to solve, and then as I've walked you through it, it turns out you really kind of know everything about it. You just have to do a simple setup, solve a problem, and when you get the solution here, you're going to have to convert the QR from days to seconds, or the Q from seconds to days, either way. But once you do, you should be able to get an answer here, 1,850 milligrams VSS per liter. Okay, and that should be less than the amount in the recycle pipe because it's essentially getting diluted into the influent pipe. Does that make sense? Did some of you kind of get close to that before talking about it, or maybe not? Okay. So again, with this problem and probably any of your any problem you solve, it's going to be very beneficial to draw your system as best you can, to really think about it at that level. Okay, so the next problem says, if in this newest system with the recycle line, the resulting F to M ratio is 0.58 milligrams BOD per milligrams VSS per day. And so the question is, what is the new ml VSS concentration? That's essentially the X in the tank, right? So I'm going to go ahead and kind of do the same thing. Draw up your chamber. I'm going to write up the equations again, and consider how you're going to solve this one. Yep.
The same as X?
No, because in the reactor itself, the question is this X prime, X not prime, is that going to be the same as X here? There's a reaction happening inside this reactor that's growing X, and we also have an exiting amount of X, so that's not actually going to be the same value here. It's a good question. Okay, so this time we're given food to mass ratio, and so probably a good idea to go ahead and look at this equation and see what you can learn from it. You have the food to mass ratio, you have a flow rate, incoming substrate, the volume, and the X. And if you think about it, we only have one unknown there, which is the X, which is what we need to solve for. So this one becomes pretty simple. Starting from here, we can just rearrange and say X is going to be equal to Q S naught divided by V times that F to M ratio. Here's a good example of why we don't want to be dealing with F to M as if that's a fraction and two variables, just one variable, because you would think to yourself, okay, I've got to multiply by M and divide by F. Then you get confused about where's M and where's F. Maybe there's a way to do that, but not, it'll come back to this ratio that was already given, right? So just keep that together. We're not going to ever need to split it. Okay, so that gives us almost everything we need. So we put in the numbers, 0.01 cubic meters per second times the S naught. This was given as 220 milligrams BOD per liter. And so some of this is just understanding what these parameters are talking about up there and ciphering through them to see what you actually need. So this said the substrate concentration of the primary effluent, and it explains further, entering the activated sludge process. So the primary effluent, what's leaving the primary system into our secondary system, which is what we're talking about today. So that's going to be the S naught here. So that's 220 milligrams BOD per liter. And we'll divide this by the volume of the chamber, which was 500 cubic meters, and then multiply that by the 0.58 milligrams VSS per milligrams BOD per day that we had. And what you'll notice here is we have days on the bottom and seconds on the top. So we have to essentially multiply the top, or multiply this whole thing, by the amount of seconds in a day, which is 86,400 seconds per 1 day. So that'll convert the units on the top into per day there. Okay, so with that, we can plug in the numbers and we should get X equals 596 milligrams VSS per liter. Does that make sense? Okay. Any issues, questions? All right.
That's like which, like, that's like that. So that question that put like the X into the derivation of X.
Yeah. So that's a great question, because really what you need, part of what you need to learn here is what is the problem talking about when it's using this jargon, right? So when it says what is the new MLVSS concentration, so that's mixed liquor, volatile suspended solids, and then it gives you the in milligrams per liter VSS. Well, the term that we describe with that unit is the X value, and the mixed liquor should kind of tell you what we're talking about is that mixture in the activated sludge chamber. So that's really the X here is what we're solving for.
The rest of the X is not change.
The rest, you mean like in the XR and stuff like that, or?
Yeah, like XR, X not. Yeah.
Well, when we changed, when we started the recycle line, there may have, we didn't have a recycle line to begin with, so yeah, those things changed, and we're just kind of starting like, here's a new system now. Here, like, what does this have to be? And in some sense, if you look at the definition of food to mass, if we know how much food we've got, and we have that ratio defined, then we have to know how much mass of microbes we have. So in some sense, it's like just even providing the food to mass ratio made it so simple of a problem that it's almost silly, right? In a way. But so it's obvious but not obvious because it's all this jargon and a new system, but it's not a very complicated problem if you've already defined that. Yeah. That should have been 550. Sorry. I think the math should work out unless I just did it wrong in the first place, but I think I just wrote it wrong. Maybe you guys can check for me.
It's still right.
Okay, good. All right, any other questions? Okay. So the next problem kind of builds on that and says, we've got that value from the previous one. that was 596. And by the way, we also, I think this one's referencing the XR, which was given earlier in the problem, was 12,500. I think it's either this one or the next one we need that. So this question says, what is the flow rate of the waste sludge line? And so, surprise, surprise, we're going to need the last equation that we talked about, or that we haven't used yet. It's the cell retention time. That's Vx over QW XW. So go ahead and give that a moment. And I want to talk a little bit about BOD after this. Okay, so this case, we're taking a look. We want to find QW. And if we take a look at our solids retention time equation, we're given, by the way, the solids retention time. So that's already in the problem prompt, essentially. So we know the value there, and we need to find, sorry, I should have labeled that as QW. We need to find QW. So we could rearrange this and say QW is equal to Vx divided by the cell retention time times XW. And then you might think to yourself, okay, well, we've got X, that was the 596. We've got the volume, assuming I can transcribe it correctly. And then we've got the cell retention time, but what is XW? Well, the XW here is the same thing as XR. What's that? And that was earlier in the problem, we saw that was the 12,500. Okay, so that gives us everything we need for this problem. At that point, we just have to plug in the numbers, recognize that the cell retention time is in days, and that should be all right. Our answer will come out to days if we leave it that way, or a flow rate in days. So QW, when we put in those numbers, should be 2.98 cubic meters per day. Okay. So, get an issue, or did I do something else? Did I get the value right there? Let's see. can double check. Anybody else getting a different number? If you do this? Okay, so let's just do this real quick. So that was 550 times 596 divided by 8 and divided by... Yeah, that is a different number, isn't it? I bet I did this with 500 instead of 550. Yeah, there you go. So my mistake carried through with my answers. 3.28. Okay, sorry about that. The units for the XR, well, if they're the same as X, then you don't. So X, if we take a look in the last problem, this was milligrams per liter VSS, and this should be the same milligrams per liter VSS. Yeah, which is basically always what we're going to use for X. Yeah, so that one, it was pretty straightforward, assuming you use the right volume. Managed to mess up again. Okay. Last part of this question is really, what's the hydraulic retention time before and after? So I'm just going to kind of breeze through this and say, well, it's technically the same, right? Because of the assumptions we made, there's no change for the hydraulic retention time. It's just V over Q, which is 550 divided by the flow rate, 0.01 cubic meters per second. And assuming this is correct, double check me real quick, but that should be 0.58 days. So I convert there from seconds to days to make it a little more manageable. So if you do that, maybe you can double check me there. All right, any questions on that? Did or did not?
It
Did. Okay, so what is the correct answer here? Well, it's 550 instead of 500. Put you on the spot.
0.67.
Okay, so we'll just say 0.64. Okay. Good, and hopefully that gives you a little confidence you can correct my mistakes as needed. Okay, so I want to talk about BOD. So let me pull up a new set of slides. I'm just going to try to get through the basics of it, essentially, before the end of class today. I might have to edit this just real quick. Yeah. I just need to make a quick copy of this to, so I'm not saving over the other class's notes. Okay. All right, so now remind me, did VJ cover BOD at all for you guys? Yes? Okay, so you already have kind of the basics. Did you do BOD calculations like downstream of kind of like a wastewater discharge? But you do know how to do like a BOD calculation in the, like a bottle, the BOD bottle sort of thing. Okay, so I'm just gonna...
Yeah, we went over that.
Okay, so I'm just going to fly through this sort of stuff. You probably, so BOD, you know the concept, it's the amount of oxygen that's going to be demanded. theoretical oxygen demand you probably talked about a little bit. It's kind of like theoretically how much oxygen could a molecule or something possibly demand. So that would be a stoichiometric thing. So for glucose, for example, for the theoretical, we're assuming we're going to oxidize everything. So if we've got C6H12O6, we're going to take some amount of oxygen. It's going to react. And since it's just carbon, hydrogen, and oxygen, we're going to get CO2 and water. It's going to be the generic reaction, and we can balance this. It would end up looking like this. I think that's correct. Yeah, so that would be the balanced equation. You could balance that, and then you could say, okay, well, we need 6 moles of molecular oxygen for every 1 mole of glucose, and we could calculate on a mass basis and say X amount of mass of oxygen for every gram of glucose, right? We could do a calculation like that. That's the theoretical maximum. So that's theoretical oxygen demand. Not very convenient when you don't really know all the different molecules and how much of that molecule there is in a sample of wastewater. So only practical if you have a very specific reaction in a very controlled situation. So just a theoretical, right? Theoretical is in the name. Then we have chemical oxygen demand. Did you ever talk about that at all? Okay, so it's a chemical method, kind of not stoichiometric chemistry, but practically hit it with acid, hit it with heat, hit it with stuff to oxidize everything, see how much oxygen comes out. Then there's BOD, stuff from the biological activity. You can split that up into nitrogenous, so the amount of oxygen required to convert ammonia to nitrite, then nitrate. It's going to take some oxygen. You can involve that part of the process. Consider the nitrogen cycle generally and where that fits in. Basically waste decomposition, right? Okay, so you already know about that. You know that how you do it is this oxygen measurement in some bottle. You prevent any photosynthesis by shielding it from light. That's why you do it in an amber vial, or you don't use this, or you cover the clear bottle with something. You let it incubate, typically 5 days. You're measuring the oxygen. A lot of times you have to dilute it, so you need this calculation. This is the calculations that I grabbed from our book. Should be about the same as what you have. So I'm going to basically skip through that. There's an example problem that I use. I went ahead and put the solutions from previous time up there. I'm going to move past that. I'm going to introduce the kind of the final concept in a moment, and we'll really cover that more thoroughly in terms of modeling it, what happens downstream, Tuesday when we come back from break. Okay, so if you have to add a big dilution, which you typically do if you've got high-strength wastewater, or if you just don't have enough bacteria in the remaining wastewater, maybe it's a disinfection sample, you have to add bacteria to your BOD bottle, right? So this is a seeded dilution. Did you guys talk about that? Maybe not? Okay, so this is essentially, we've got a very dilute BOD measurement, means there's not enough bacteria there to begin with, so there's not going to be any growth of bacteria. So even if there's BOD substances, you need bacteria there. So you have to add the bacteria, and when you do, you add some organic matter because you have to have that organic matter to keep the bacteria happy. So you add BOD on accident, or consequentially, you didn't want to, but you kind of had to. So the way that's going to happen in a seeded BOD test then is you've got, like 300 milliliters total. So you've got some total volume. And then what I'm going to do is I'm going to say, well, we've got some volume. Of course, these are going to mix. So I'm just kind of using this to illustrate. Some volume of this is going to be your dilution water. Should be kind of you already covered that essentially. And the fact that you've got some volume, some smaller amount, that's going to be your wastewater. So that's the concept of a diluted system. But if you're adding some BOD in the volume of the dilution, in addition, because if you can, you just do pure water and that's that. But if you have to seed it, then you have to add some BOD with that, or there is some BOD. So that's where this calculation is going to come from. Essentially, we take our BOD of the mixture, so BOD5M for mixture, that's going to be essentially this bottle here, you measure the BOD in that. So that's your mixture, And then you also have to measure on the side a second bottle where you just test the dilution water to see how much BOD is in your dilution water. And then it's a matter of, okay, well, if you're solving for BOD of the wastewater, it's going to be a function of those two. So this is an experiment to test, or a measurement to test the BOD in the dilution water. So that's one bottle. Then you have a second bottle where you take measurements and get a value for the mixture of the two, and using those two, you can find the value that you wanted to calculate right here. So I'm just going to write that's calculated. So ultimately, that's what you're interested in, right? The BOD in your wastewater sample, for example. You have to measure these two values, and then you find that it's just like we were doing earlier. It's the mass times volume here. That's giving you your mass. The mass is constant across these, and so you can solve that way algebraically. Okay, I'm going to just kind of fly through this. There's a derivation here that comes from that equation that we just looked at. The BOD of the mixture times the volume of the mixture is equal to the two components added together. It's simple. You can derive an equation just for BOD of the wastewater as a function of those two BODs and as a function of the dilution factor. There's a tiny bit of algebra magic, not really magic. It's just a little bit of fraction stuff that gets put in here to simplify. I'm just going to skip that for you. It's essentially taking 1 minus p is a fraction compared to p is a fraction. It's just a little bit of manipulation, and you get there. It's a nice, handy equation to use if you're dealing with BOD of wastewater when you have seeded dilution water. Okay, that's the point. So this is the kind of an equation for what we call seeded dilution water. Okay, so that's an equation. Again, that's going to be on the equation sheet that I'm going to post to Moodle. Okay, from there, yeah, okay, so this is just rehashing that a little bit. We need two experiments essentially, and just as a reminder, you can describe those two BOD values as an initial minus the final. And in the terminology from the book that I used, you can write the BOD or the dissolved oxygen as BI and BF for the dilution water. It's just the DO in one and the DO in the other, right? It's just the thing in terms of dissolved oxygen measurements instead of just the BOD itself. Okay, there's an example problem here. I'm going to skip this for now, but feel free to take a look. When we talk about modeling BOD downstream, I'm just going to talk for a moment about this to kind of tell you what's coming. I think you probably have one of these problems in your homework assignment that I've posted. So to give you a little context, feel free to look ahead in this set of slides for a little bit more analysis in that direction. But essentially what we're going to do is take a look at what happens to the dissolved oxygen content in a river or a stream after you've discharged some water that has some oxygen-demanding substances in it. So you have a wastewater discharge. It's got a little bit of BOD in it. So what happens in the river? Well, if you measure the dissolved oxygen as a function of time or even distance, as the flow is kind of the same speed the whole time, you can measure that, and you can essentially model how far downstream or how long a time from now will it reach a minimum dissolved oxygen content. That's going to depend on how quickly oxygen is being added back into the water from the air. So if it's like a waterfall, there's plenty of aeration, it's going to be adding a lot of air back into it. If it's a slow, stagnant bayou, chances are it's not getting re-aerated very quickly, especially if it's really hot. So it's going to depend a bit on the dynamics of the system. And essentially, most natural waters have a slight deficit from saturation. Whatever the saturation happens to be at the given temperature, it is temperature dependent. This is going to often be something like 8 to 10 milligrams per liter. maybe higher if it's colder. So essentially, most rivers, waters, natural waters will have a small initial deficit. So that's going to be kind of the difference here. You can look at this oxygen deficit as a comparison of saturation to the current oxygen level in the water. So a small difference is a small deficit, larger difference is a big deficit. So this oxygen deficit at the maximum is really what we're looking for to understand how bad is it going to be if the wastewater is this dirty, has this amount of BOD. So that's kind of the point, is how bad does it get? Is that still safe for the fish? Is that going to cause a fish kill? Where is that going to happen? And this is especially important if you have multiple wastewater discharges, right? You want to be able to say, okay, well, this wastewater treatment plant is 2 miles upriver from this one, and then this other stream merges, and we know that one's got very, just naturally not much, naturally high oxygen deficit. So then we might have a big problem after that. You can kind of see how these systems are going to merge, and we would want to be able to model this type of a system to understand what's going on. So we're just going to take that basic system, one wastewater input, looking at that sag curve, this is the oxygen sag curve, and do an analysis that way. We can kind of think of this in terms of the amount of organic carbon. You can take TOC measurements, total organic carbon, to kind of estimate that. So that's one thing you could do. And if you were to do that in a river like this, you would watch as that total organic carbon is removed by this biological activity through the respiration and everything. That will decrease over time, and that will correspond to the oxygen consumption over time. So the oxygen consumption will be high at first as all this stuff is readily available for the bacteria to eat. They're going to be consuming it. And so that is kind of that food, that substrate that would go into this type of a system. Okay, so in terms of BOD, if we do a mass balance on the system, essentially a stream or a river will act similar to what we call a plug flow reactor. I know you guys didn't really cover that, but we'll talk about the math. It's, we'll have equations that kind of show us what it is. It's essentially, we're taking a look at a reaction that's occurring, and it's just going to be occurring over time. As we can think of just one chunk of water, it's going to flow downstream. Whatever happens to that particular chunk of water, since we're going to assume we're at steady state, the same amount of stuff's coming in as is leaving. Like, we're not changing how much wastewater is coming in, for example. It's just things are constant, and we can watch whatever happens to that one chunk of water is going to be the same thing that happens to the one the day before and the one the day after, assuming everything stays the same. So we're going to get a kind of a reliable picture of the dissolved oxygen according to that BOD input to the system. Okay, so I'm going to stop there. We'll talk more about that when we come back. Have a good Thanksgiving. Happy Thanksgiving. Good luck on any remaining exams or final or assignments.